This is Saxon's Trigonometry, Lesson 3, beginning on page 26. Part A is about Pythagorean theorem, which I accidentally went over in lesson 2, but that's okay. We're going to review it again. So on the top of page 27, they give an explanation as to why Pythagorean theorem works the way that it does. But basically, you should remember that it has to do with a right triangle, and Pythagorean theorem only works with right triangles. So if we label this side as a 3, this one as a 4, and this one as a 5. Mathematicians in the past basically discovered that if you represent the 3 as a rectangular or square shape, actually, because it's going to be 3 by 3, and you do the same here on the side, making this one a 4 by 4, and you count up how many squares do you have here. Well, that's obviously 9, and that's the same as 3 squared is 9. This is 16 squares, which is the same as 4 squared to 16. And when you add those together, you get a total of 25. And would that be what you get if you create a square here, which is going to be 5 by 5? Yes, 5 squared is 25. So that's how we have determined that Pythagorean theorem works. And so the Pythagorean theorem basically says a squared plus b squared equals c squared. And the c must always be the hypotenuse, which is the side opposite the 90 degrees. And you will want that in your notes if you do not have it memorized well, that this is the Pythagorean theorem, and it is a squared plus b squared equals c squared. The c must be the hypotenuse. Now, in part B, they begin to talk about triangle inequalities. So if it is not equal, it falls under the category name of inequalities. Something is greater than something else or less than something else. And so if you look at the middle of page 27, they show you other triangles with the squares that are marked and how these things work. So if you have a right triangle, when you square your two sides, it will equal, making it an equality. But what happens when the sum of the two sides is greater than this side, the hypotenuse side? You will have an acute triangle. So if a squared plus b squared is more than the c squared, it's an acute triangle that you actually have. If a squared plus b squared is less than the c squared, then you have an obtuse triangle. And we talked about those in the other lesson and what they look like. Now, this feels backwards to me when I read it, because I feel like if the two legs are more than, it should be an obtuse triangle. So basically you just need to make note that your instincts here are going to be backwards if they're anything like mine, and these are the actual formulas. So in example 3.1 at the bottom of page 27, it says the lengths of the sides of a triangle are 7, 5, and 4. Is the triangle a right triangle, an acute triangle, or an obtuse triangle? So you will want to identify the two smaller ones, and they will act as the legs. The larger number will always act as the hypotenuse. So 5 squared is one of the small ones, plus 4 squared is the other small one. And how does it compare with 7 squared, which is 49? So 41 is comparing to 49. 49 is larger. So we are saying that the hypotenuse is larger than the other two, which makes it an obtuse for that answer. Obtuse triangle, to be precise. Now we turn to page 28 and we talk about section C, which is similar polygons. At the top of 28, you see a series of shapes that are not polygons. In A, it is not a polygon because and these are not going to be drawn exactly like the shapes, but it's the same similar idea. You have lines that crossed. That's the same problem in B. It crosses. You also have this one, which is not a polygon because of the curved side. And in D, you have a shape, again, I didn't draw it exactly as they did, but it has an open gap. And so if any of those things happen, you don't have a polygon. The next set of pictures that they show you labeled E through I are polygons. The first one is a triangle. It's all pointing outward, and that works fine. In F, you've got a shape. Oh, sorry, let me try to straighten that up a little bit. That in one place caves inward, forming a cave, not all pointing outward. And so they've labeled that there in the book as a cave. So if they're all pointing outward, we call them convex, and this one concave because it has a cave in it. G is a rectangle shape, so it would be convex, all corners are pointing out. H and I are getting a little more specific. They are all convex, all corners are pointing out. And in H, all of the sides are listed with the tick marks as being the same length. So we use that word equilateral. Lateral being sides, equal, all sides are equal. That's an equilateral polygon. Just to make sure you're seeing it, they're all marked with those double tick marks, like so. Now my scale is not correctly equilateral polygon, but you get the idea. And the final one in I is an equiangular polygon because all of its angles are marked as the same. And we will have, if it's equilateral, as we've talked about before, angles that are opposite equal sides are going to be the same. So if we have it equilateral, it's going to be equiangular, and in reverse as well. All right, their next section is where they go into the preciseness of what forms a cave and what makes it convex. I think you've got the idea already. And then at the bottom of page 28, they show you two shapes that have angles that are marked the same. This one's kind of short, and again, not to scale. And then you need another one that is basically the same. It's off a bit, but so this one's labeled 4, 3, 2, and 5. This angle is marked with a single tick mark to match with this one with a single tick mark. This one with a 2 tick mark, this one with the matching 2, this one, oh, no, that's right. This one with a 3, this one with a 3, and this one is not labeled, but by default, if 3 of them are going to be the same, that 4th one is going to be the same. They could have marked it with a 4, but they didn't. So in this one, it is labeled 5.6, 4.2, 2.8, and a 7. So what happens when we have similar triangles because they are the same shape, but they are not the same size because this 4 is not identical to 5.6, but they are similar, mathematical symbol, the single squiggle, when I put the equal sign under it, we've made it congruent, which means same shape and size. But these are similar, same shape, but different sizes. And when we have similar shapes, we form, they share a scale factor or they form a proportion. Both are truthful statements. So a scale factor would be whatever you multiply 4 with to turn it into 5.6 will be exactly the same number that you would multiply 5 by to turn it into 7. So if you check that out on your calculator, you would determine that the same number is getting filled in here. The same as 3 times whatever that scale factor is gives you the 4.2. You can also just solve for the missing pieces by doing, as I said, the proportion. So okay, here's the better way I'm going to say that. We're not solving for a missing piece, but you can also find the scale factor by doing the proportion. So it would look like this. 4 compares to 5.6 the same as 3 compares to 4.2. If I multiply 5.6 by 3 and write that number here, it should be the same number I get when I do 4.2 times 4. And then that's the similarity number. On the middle, or in the middle of page 29, you see that they list scale factor, and they show you an arrow above their SF. Now, this is not trying to say ray, and that can be confusing. In this case, the direction that the arrow is going is trying to tell you from this shape to this shape is a scale factor. From this shape to this shape is a different scale factor. So let's say this scale factor going this direction happened to be a half. Then going this direction, so I'm going I don't want that. With these numbers, it doesn't work, but okay. If I'm saying that this is a half, then this is actually a larger shape than this one. And so I would take a larger number, multiply it by half, and get a smaller number to match on this side. When I'm doing scale factor the other way, it's basically flipping that fraction and making that scale factor 2. So if I take a smaller shape and I double it, I should get to the larger shape. So that's how that scale factor symbol works there. All right, on to section, just a second, let me double check this dark wordage here. The measures of corresponding angles must be equal and the lengths of corresponding sides must be proportional. Yes, that is basically what we started off saying. If we have the angles that are marked to indicate that we have similar shapes, then you will deal with a scale factor for their sides. They're going to be proportional. All right, part D is similar triangles. And they have the bold words here that mathematicians have decided to define similar triangles to be triangles whose corresponding angles have equal measures. And so this goes back to that similar symbol that I just said. In example, okay, well, they have some other dark words right before example 2. They're reiterating what I just said. So let's move to example 2. And we basically have some intersecting lines and we're forming some triangles. This is labeled 5, 4, X, 6, Y, and 7. And then they have marked some of the angles. So this one has a double tick mark. This one has a double tick mark. We know that they are the same. These two are labeled with a single tick mark, but even if they weren't, I would know that they are the same because they are vertical angles. And if two angles in a triangle are the same, it implies that the third angle must be the same. So we have similar triangles, and when we have similar triangles, we can find the missing pieces by doing the proportion. Now be careful here as you line this proportion up. So if I choose to use the 5, it is between the double and the single tick mark. What is the number on this triangle between the double and the single tick mark? That is 7. So the 5 compares to the 7. 4 is between the double tick mark and the none. So between double and none is the Y. So if I can cross multiply and solve that proportion, I have that one. I'm going to continue here to get the last piece just set up, which is X between the single and the none. Between the single and the none is the 6. So to solve for the Y, I would cross multiply here. 7 times 4 divided by 5 will give me Y. So Y equals 28/5. And then if I ignore this piece, I can do the cross multiply here to solve for the X. 5 times 6 is 30, divided by the 7 is X. And again, you'll notice that I left both of those in improper fractions. You can make them mixed numbers. It really doesn't matter in which way that you leave it. Okay, example 3 on page 31 is very similar to what we just did. I don't know that you necessarily need to see. It's just another proportion solving out. Example 4, however, on page 32 is very different. This is giving you a triangle, and then it's cutting a smaller triangle on the edge. So this shape is not a triangle shape. We won't actually use it. So things are labeled 4, 6, A, B, and C, and this one is a 4. And they have clarified that this angle is 90 degrees. This angle is 90 degrees. So both the large and the small triangles are right triangles, so these two angles match up. Regardless of whether they label it or not, they did label this as a single tick mark. It is the shared angle, the same angle in both of those triangles, so it would have to be identical in both. And if I have two angles that are the same, the third is implied to be the same. Therefore, I know I have similar triangles in the big and the small, and I can set up proportions to solve. I guess I should stop and say that your book sometimes goes through scale factor, and if you prefer scale factor to this method, that's fine. I just use the one that I like, which is the proportion, because it feels fast and easy for me, but feel free to find the scale factor and use it to make your adjustments if you prefer that. All right, so here for this small one, I have the 6 as the long side. What is the long side of the big triangle? I need to find it myself. It is 6 plus 4, making it 10. Then I have A as the hypotenuse for the small one. What is the hypotenuse of the big one? A plus B. And then I have 4 as the smaller side, although it doesn't look it, and then that matches with the C. Now I can cross multiply to get C very easily here and do 40 divided by 6, reduce the 40 and the 6 down to 20 and 3, so C equals 20/3. That's easy enough. I'm double checking the answer they have here. Oh, this one is very long. Yeah, 20/3, there we go. Okay, so C equals 20/3, and I can box that answer. But to get A and B, even if I use this as my proportion, I have two letters, an A and a B in the problem, so I can't solve for them separately. When this happens, I know that I need to go to one of the original triangles, and I should be able to Pythagorean theorem it. The big one has the A plus B and a C in it, so Pythagorean theoreming here isn't going to help. But the little one has a 4 and a 6, and then I can solve for the A as the hypotenuse. So 4 squares to 16. 6 squares to 36, A squared plus B squared equals C squared, which is my hypotenuse. So in this case, that's going to be the A. So then 3, 4, 52 is A squared. How do I get A alone? I square root both sides in order to cancel out the squared, leaving me A equals the square root of 52. Now, that is a decimal if I put it on the calculator and turn it into a decimal. Or I can simplify it, which is more likely how the Saxon book is going to do this. And so you may have to, if you're using their answer key to check an answer, you may have to convert it this way in order to make sure that you are right. So let's split this into a tree form just so that I can see what are the prime numbers that give things. So whatever you see that divides into 52, you do. I tend to see even numbers going in. So 2 divides into 52 26 times. Let me make sure I'm on the right track here. And then 2 goes into this one 13 times. 13 is a prime. My 2's are primes. Whenever I have a set of 2, it requires 2 identical numbers to move to the outside of a square root. So if you picture these together, you're basically saying, what is the square root of 4? And then the square root of 13 is left beside it, if you write them separately. And so the square root of 4 is 2. So if you have 2 sets, you just automatically pull that single number out, making this 2, and the root 13 is stuck in the radical. It doesn't have a match to pull it out. So I now know that A is 2 root 13. Or you may have it in a decimal, but your book is pretty much always going to have it with a root, not as a decimal. Now that I know A, we're going to plug it in here in both places. And now we have enough that we can solve for b. So we're ignoring this piece and doing the cross multiply here. I'm going to start with the easier one. 10 times 2 root 13 is going to give you 20 root 13, and that will equal the other distribute, which is 6 multiplying with these parts. So first, 6 is going to multiply with the 2 root 13 and become 12 root 13. And then the 6 has to distribute also with the b and give you 6b. Now this you can solve. These are like terms because they both share the root 13. When I move this one to the other side, we'll minus it to move it because it's implied as a positive here. So minus 12 root 13 gives us 8 root 13 equals 6b. And finally, we divide by the 6 to separate it from the b. And so 8 divided by 6, actually, let's write this over here. B equals, this is merely going to reduce down to 4 root 13 over 3. And that is B. So we have B, we have A, and we have C. We have solved for all of the parts that they asked us to solve for. In example 5, the final example of this lesson, we have again triangles that are shared, and this comes straight down. So this is splitting it into, technically there are 3 triangles here, the one on the left, the one on the right, and the big one. And so we are going to need to solve this a little bit differently. This is labeled A. This is a capital M for the point on the side. This is a 4, 8, K for the point, lowercase b, lower h for that height, and this is labeled as 90 degrees. This top corner is labeled as 90 degrees, and they have labeled this with a single tick mark and this one with a double tick mark. And so they are not showing any other tick marks that are the same. So I don't see things that are labeled up. So here is how I will treat when I've got 3 triangles that I'm dealing with. I like to do a chart, and eventually you might instinctively be able to do it without the chart, but this just is an easy way to organize things. So what we have is the big triangle, the I do it different ways, it doesn't really matter, right triangle, left triangle. We also will have the little leg, the big leg, and the hypotenuse. And these will be the parts I need to fill in. So from the big triangle, the overall shape, what is the smaller of the legs? And that would be, so here's our 90, so we know this one is the hypotenuse. The little leg, the shorter one, is A. That means the bigger leg is the B, and the hypotenuse is this 8 plus 4. Now the triangle on the right-hand side, its little leg is the H, its big leg is the 8, and it's, if this is 90 here, this implies a 90 matching this side, so the hypotenuse will be B. Then the one on the left, the little leg is the 4, the bigger leg is the H, and the hypotenuse is the A, opposite that 90 degrees. So now that I have my chart, I can choose any set of these to help me set up my proportions. So if I want to solve for the little a, I look for row and columns that have the A, one here, one here. So we're going to ignore the middle one and concentrate on these two, and then of course we don't need this one either. So here is the proportion that I'm going to use because it's the ones that have the A's. So that gives me A over 4 equals 12 over A. And that I'm going to solve by cross multiplying. So 4 times 12 is 48. A times A is A squared. How do I remove the squared? I square root both sides. That leaves me with an A here and the square root of 48. That is not going to go to a single number, so I'm probably going to do that splitting it up. So in this case, rather than going by a 2, I'm going to go by a 4 because that makes that 12. Then my 4 splits into 2 and 2, my 12 into 2 and 6, and my 6 to 2 and 3. Everywhere I have a set of 2's, I know I'm pulling a 2 out. So that's a single 2. I have another set here, making another 2 pulled out, and a 3 stuck inside the root with nothing to help it. So my A is 4 root 3. Now we need to do the same thing and find the B. So here's a B, here's a B. I don't need here or here. So my proportion is B over 8 equals 12 over B. And identical to what we just did over here, B times B is B squared. 8 times 12 is 96. Square root that and split it up. 3 will definitely go in. You can do it down or sideways. I'm just running out of space. So let's see, that goes in there 32 times. 2 goes in there 16 times. I'm shifting gears here. 2 and 8. 2 and 4. Okay, since I'm totally on the edge of the page there, we're definitely going to have to finagle just a bit. There, now you can see it. So this 4 is going to be a 2 on the outside because it's going to split to 2 and 2. So I know I have a 2 here, a set again here, that's another 2. And then I have this 2 and this 3 not with mates. So that's going to keep them as and multiply them back together to a radical 6. And so this means B equals 4 root 6 for that answer. Okay. And the final one we haven't done is the H. And I'm going to try to keep it on this page, so I'm going to try to cram it back up here. So for this, I don't have an H here, so I'm going to use here, and I don't need this one. So it's going to be H over 4 and 8 over H. And then cross multiply, that's H squared equals 4 times 8, 32. Square root to cancel it. So we know we're going to split this up. H equals 2 again in here 16 times, 2 and 8, 2 and 4, 2 and 2. All right, so we know we have a set and a leftover 2. So we have 2 times 2 pulled out to a 4, 1 root 2 left stuck alone. So the H is 4 root 2. And those are the parts A, B, and H that they wanted us to solve for in that example.